Hello, everybody. Welcome to our 11th webinar on CPT dissipation tests, theory and practice. Just a side note, if we encounter any kind of technical problems as we experienced a little bit last time and you get kicked out of the webinar, please just wait a moment and then sign back in as it'll come up again. But hopefully that won't happen. And I'll be happy to write down your questions using the chat feature so that Dr. Robertson can answer those at the end for you. And we'll go ahead and get started. Here's Peter.
Thank you, Kelly. Well, welcome everybody to this webinar number 11, the 11th in our series. And the one today is about dissipation tests. And so I've given it the title From Theory to Practice. So we'll talk a little bit about the theory and then move on to some practical considerations. So just a reminder that most things I'm going to say are in the CPT guide that you can download from a variety of websites. And again, just a reminder about what the cone penetration test is. It's a probe you push in. Typically you measure at least the tip and sleeve friction, but increasingly added now pore pressure. And it's the pore pressure that we're going to talk about today. So it's often measured in this U2 location just behind the shoulder, although in the old days it used to be on the face of the cone, and you'll hear me mention that, and that's often referred to as the U1 location. But quite often it's measured just behind the shoulder, the U2 position. So here's an example of a CPT profile. It's from an old publication with Professor Campanella. That was 30 years ago. And it was from the Fraser River Delta, just south of Vancouver. It was the well-known research site that the University of British Columbia had, which was the McDonald's farm. And it was an old abandoned farm, so it was quite often referred to as Old McDonald's Farm. And it was a sort of an ideal site. It had sort of 13 meters of sand over essentially a normally consolidated marine clay. And so you see the cone profile here, sand over soft normally consolidated clay. And so in the sand, the water table is up around 1.5 meters below the ground surface. And up in the sand, you can see that it's a fairly clean, free draining sand, so there's no excess pore pressure. So of course there's essentially no dissipation test here because it's free draining. And so there's no excess pore pressure. And in this particular case, it is roughly hydrostatic. And then when you enter the normally consolidated clay, it generates large excess pore pressures, you know, three to four times larger than the hydrostatic line. And this particular case, a dissipation test was done at 20 meters. And so this is what the dissipation test looks like. Apologize sort of for the mixed units. You can see it's collected in pounds per square inch, PSI, so I've converted it to kilopascals. So it starts at about 86 PSI, which is almost 600 kPa, and then progressively dissipates as a function of time down to equilibrium. And in this particular case, it's at a depth of 20 meters, and the water table is a little over a meter down. So there's about 18.5 meters of head of water, which is about 186 kPa. You can see it's marked there. And so you can see the initial excess pore pressure, which is defined as the initial pore pressure minus the equilibrium, and that dissipates with time. And so you can see immediately that the two things you get from a dissipation test is that if you do it until 100% of the pore pressures are dissipated, you can get the equilibrium pore pressure at that depth and at that time. And then also you get the rate of dissipation, how quickly it occurs, which tells you about the consolidation characteristics of the soil. So dissipation test, it's useful. You get two primary things. You get the equilibrium pore pressure, and as I said, at that location at that time, obviously if the groundwater level fluctuates with time in the seasons, then U0 will fluctuate. So at the time the test was done and at that depth, you get that piezometric pressure. And from that, of course, you can determine the piezometric profile and determine whether or not it's hydrostatic. And the one I just showed you essentially was hydrostatic. It's quite close to the ocean, and so it essentially is hydrostatic. And you also determine the piezometric surface, or sometimes referred to as the groundwater level. And in that particular case, it was about 1.5 meters below the ground surface. And then the rate of dissipation is controlled primarily by the coefficient of consolidation, and primarily in the horizontal direction, so it's given the subscript h. And of course, that in itself is influenced by the permeability of the soil, or the hydraulic conductivity, also in the horizontal direction. And we'll talk a little bit about the theory about why it's the horizontal direction. And of course, it varies by orders of magnitude, since both coefficient of consolidation and permeability vary by orders of magnitude. Then the rate of dissipation will vary by orders of magnitude, from very fast to very slow. Now, when you get high permeability, like that clean sand, there's no excess pore pressure, so the pore pressures are essentially dissipating during the penetration process, so there's no dissipation curve, and so the dissipation is very, very fast. It's only when you get into fine-grained soils where the permeability begins to drop low enough that you do develop excess pore pressure, and the penetration then becomes essentially undrained, and then of course when you stop it, it dissipates to equilibrium. So let's talk briefly about equilibrium pore pressure. You do get this U0 value. So you can identify the general flow regime. And the first one I showed at McDonald's farm there, it's essentially hydrostatic, so there's no flow. There may in fact be very slight horizontal flow, but there's no vertical flow. But of course you can have upward flow. For example, if you encounter an artesian layer, like for example a sand layer that's under artesian pressure, and so there's sort of essentially upward flow, upward vertical flow. And then likewise you can have downward flow, and I'll show an example of that shortly. What's interesting is when you do a dissipation test, even if the filter element is not 100% saturated during the initial stages of a dissipation test, if you are significantly below the water table and the equilibrium water pressure is a relatively large positive number, then during the dissipation, any air bubbles that were in the filter element or in the pressure sensor, they will slowly go back into solution, and the element will in fact become 100% saturated by the time you get to equilibrium, if the equilibrium pressure is a positive number, if you're below the water table. And then in general, I do recommend that it's useful to do at least one dissipation test per CPT. And often, if you're doing it because you primarily want to get a handle on the groundwater level, then of course it's useful to stop in any sand layers, because either it'll be free draining during the pushing, or that it will dissipate very quickly, and maybe you only need to wait no more than maybe about a minute or two, and you'll get to equilibrium very quickly. So you can get that equilibrium water pressure very quickly if you stop in sand layers. If you don't have any sand layers, then sometimes it's useful to stop, say, at the end of the sounding, because you're going to be stopping anyway and getting ready to pull out, and so that's a useful time to maybe spend a few minutes and do a dissipation test to get an idea of what the equilibrium water pressure is like. And I'll talk a little bit about, well, how long does it take? So here's an example, and it's an example of slight downward flow. This is actually from a tailings deposit. So 40-meter deep tailing deposit, well, 37-meter deep tailings deposit. And it's a mixture of coarse grain and fine grain. And you can see from about 18 meters down to 26 meters, it's mostly fine grain tailings. In fact, all the way down to 35, with a little bit of sandier region around 27 to 29 meters. And you can see from the pore pressure profile, large excess pore pressure in the fine-grained tailings, and then essentially equilibrium, or close to equilibrium, in the coarse-grained sections, and then back into high excess pore pressure in the fine-grained tailings. And so a number of dissipation tests were done. We're just showing the one at 19 meters here. So here you can see the dissipation. It happens to be plotted as a function of square root time, and I'll explain that a little bit later. But a number of these were done, and this little plot on the side, you'll see that from the software later, is if you've done a number of dissipation tests and then interpreted them and input the measured equilibrium water pressure, these inverted triangles, then you can see relative to the assumed hydrostatic, they're a little bit lower. And so I've marked it back here for a little bit of clarity. The red line is essentially joining up the equilibriums, or the projected equilibriums for some of them that didn't quite reach 100%. You can see it's slightly less than hydrostatic, so there's a slight downward flow. not uncommon in a tailings deposit because tailings are often being deposited into the pond with water, and then that water is draining down and sideways out of the pond, and so there's a slight down and often horizontal flow. So dissipation tests to get equilibrium come in many forms and in many types. So down the bottom left-hand you can see a relatively rapid one. It's from a negative value rising up to equilibrium, about 4 minutes. The next one, say, about 10 minutes, and then 13, and then 33 minutes. So quite a range just to illustrate what they look like. There are many theories that have been developed over the years. Back in the early 60s, a number were put together, and then Tortenson in 77 probably did the first work where he did a nice little piece of work using cavity expansion, both cylindrical and spherical cavity expansion, to try and mimic cone penetration, and assuming just a simple elastic, perfectly plastic soil model to come up with some dissipation curves. And then in the early 80s, Balik and Lavedou did a very nice piece of work using strain path method, which was a very novel theoretical interpretation, assuming uniform strain paths as the soil flowed around the cone as it penetrated. But then in the late 80s, early 90s, Holsby with a graduate student, Tay, Holsby and Tay, and then Tay and Holsby had a couple of papers, and they took the strain path method, sort of developed it a little bit further, added in a slightly different numeric constitutive model, and then added in a little bit of finite element to get equilibrium and sort of updated it. And what was interesting is the solutions by Tay and Holsby ended up being very similar to the ones by Tortenson. And then in the late 90s, Professor Main, with one of his students, Susan Burns, developed another solution, also based on cavity expansion, but this time combined with critical state soil mechanics constitutive model. And probably the two most significant works are these latter ones, Holsby and Tay, and Burns and Main. So those are the ones I'll briefly talk about. But the key findings that came out of the theory, in general terms, is that dissipation is controlled primarily by the horizontal coefficient of consolidation. Essentially, when you push the probe and you develop these large excess pore pressures, and then they will dissipate radially away. And so hence it's controlled by the horizontal coefficient of consolidation. And that the initial distribution of excess pore pressure has a major influence on the process. And you'll see later that that's one of the complexities of the theories, is trying to come to grips with what that initial distribution is, particularly when you're measuring it either on the face of the cone or on the shoulder of the cone. They're in quite a complex location. In simple terms, it's sort of this sort of boundary between spherical cavity and cylindrical. Spherical cavity expansion representing sort of essentially the tip, and then cylindrical cavity expansion representing essentially the shaft of the cone. So it's that boundary between the two that complicates life. Consolidation is predominantly in the recompression mode. So you can imagine that when you push the cone in, you develop large excess pore pressures, so the effective stress drops, and then when you stop and a dissipation test occurs, those pore pressures dissipate down, so the effective stresses climb up, and so you're in the recompression mode. And most of the theories show that by the time you get to about 50% dissipation, you're getting back into the normally consolidated mode. And you'll see later that that's why a lot of the interpretation is often focused around that 50% mark, to make it a little bit easier to handle the interpretation. Also, the theories realize that the relative stiffness of the soil, often referred to as the rigidity index, which is the stiffness divided by the strength, affects the interpretation. Basically, the stiffer the soil, the larger the zone of influence, the larger the plastic zone of the soil, so the larger the zone that you have these excess pore pressures. So the stiffer the soil, the larger the radius over which excess pore pressures get developed, and therefore, the longer the drainage path is, and so that influences the rate of dissipation and hence the interpretation. Useful to keep in mind that the dissipation, and you'll see the theories, the end result is somewhat similar to the traditional one-dimensional consolidation that we're used to from lab testing. In the lab, of course, you do one-dimensional consolidation, and we interpret the data often in a log time or a square root time interpretation to get the times that we then plug into the theory. And that's exactly what we do with CPT dissipation tests. So let's briefly review the strain path method that originally Balik and Leverdew did, and then updated by Holsby and Tay. And it generally fits sort of a simple soil behavior where you have large excess pore pressures and they monotonically decay with time. And often it's applied at the 50% dissipation, and that time is often referred to as the T50, so it's a single point, and so that means there's a simple chart that you just take this T50 and go to the interpretation. And you need an estimate of this rigidity index, and it can handle different locations, and you get this very simple chart. And so this is what the theory produces. You get this theoretical degree of consolidation, U, which is 1 minus the change in pore pressure over the initial excess pore pressure. So it goes from 1 to 0, starting off at 1 and then dissipating down to 0, or starting up at 100, 1, yeah, going down to 0. Keep it that way. And then there's a theoretical time factor, T. And the original work showed that it was a T, and then Holsby actually sort of suggested a modified time factor that incorporated rigidity index. And when you use the modified time factor, instead of getting a family of curves, you got a single curve for a wide range of rigidity index. So he embedded the rigidity index into the theoretical time factor instead of having different curves. And so you can see here that when you come in at the 50% mark, you get these theoretical times. And this slide was I got from Professor Main, so that's nicely animated there. And you can see that for the pore pressure on the shoulder, this U2 location, the theoretical modified time factor is 0.24. So here's the equation. The coefficient of consolidation is this theoretical T50 times the radius squared times the square root of the rigidity index divided by the measured T50. And 0.245 is the theoretical T50 for the U2 position, and it's 0.118 for the U1 position. And R is the radius of the probe, which for a 10 square centimeter cone is 1.78 centimeters, and for a 15 square centimeter, just a little bit larger at 2.2 centimeters. So back in '92, we wrote a paper where we looked at these methods and looked at data from around the world. And out of that came up with this sort of simple chart where we plotted T50 on a log scale on the horizontal axis, and then the coefficient of consolidation, CH, on the vertical scale, also on the log scale. And then Tay and Holsby's solution end up being just simple straight lines for a family of rigidity index. And you'll see later that rigidity index generally varies normally from about 20, maybe up to as high as 500. So here's the range that you see expressed. And so for a 10 square centimeter cone, you would just get the T50, like here, for example, at 1.5 minutes, and you'd come up and select the rigidity index and then go across and get your CH value. So it's very simple. And if you're using a 15 square centimeter cone, you then take that CH value and multiply it by 1.5 to account for the different radius. Here's an example. This is that tailings example again. Remember I showed you the profile and dissipation test at 19 meters. And here I'm showing it as a log time. You see this nice logarithmic decay and the 50%. So normally it like starts off at the equilibrium is at 100. It started up around 550. So halfway between is about 340-ish. And so you come across T50 is 85 seconds, or almost a minute and a half. And so here's that data again. The left-hand plot is on a log time. The right-hand one is on a square root time. So when you've got a full curve, you've got this nice monotonic decay on the log time. But of course, you can see that T100 is over 2,000 seconds, and T50 was 85 seconds. So there's a 20 to 30 fold difference. So you get to T50 a lot faster then you get to T100. So if you don't need to get to equilibrium, then quite often you can stop at a little bit short of the 50%. Now, one of the dilemmas when you do that with the log time is it's hard to extrapolate where T100 is, and therefore what the equilibrium is. A little bit easier for the square root time, so it's a little bit better for short dissipations, and we'll see that later. And actually, the Tay and Holsby solution gave it in terms of the slope of this straight line on the square root time. So theoretically, they observed that in terms of square root, it essentially came down as a straight line for a period of time and then curved over to equilibrium. And that you could take the slope of the straight line portion and use that as a way of the interpretation. And so that is an alternative, and you'll see that later, that's actually quite a nice way to do it. For complex dissipations, that's not a bad way to get it. And so in that 92 paper, we took data from a number of sites around the world. This was usually samples and that were then taken to the lab. Consolidation tests were done, mostly in the vertical direction, and then some assumption of switching it to the horizontal based on the ratio of vertical to horizontal permeabilities was made. And the data is compared to the theory, and you can see a pretty good fit in general. There are some points down here that begin to go off for a bunch of reasons. Some of them are stiff, sort of fissured clays. Others, it's not quite sure why they're off so much. But in general, most of the data fits reasonably well to Tay and Holsby theory. Now, the rigidity index, you need to get some handle of what it is. And conceptually, the concept behind it was shear stress against shear strain, and you've got the undrained strength value. And if it's the assumed elastic perfectly plastic model is that the rigidity index is the modulus over the strength. But of course, real soil behavior is nonlinear, and so it's a little bit more subjective about what is a reasonable representation for the rigidity index. And Professor Main had this slide, and what's nice is Paul showed this little reference strain down here, which is 1 over the rigidity index. So if you assume a rigidity index, 1 over that value is the strain, and that will give you some sense of the value. So if you assumed a rigidity index over 100, 1 over 100 would be about 1% strain. So not a bad number for a soft clay. And then Caveni and Mitchell back in the 80s did some lab tests, and they looked at this, at least rigidity index where it's defined as the secant shear modulus at 50% of the strain to failure. And so they plot this essentially rigidity index against OCR for a range of soils, and you can see that it varies with plasticity index, which is often sort of a proxy for friction angles. So low PI materials often have high friction angles, high PA materials often have slightly lower friction angle. And so critical state soil mechanics actually does capture that general trend quite well. So you can see it varies from maybe as low as 20 up to as high as 3 or maybe as high as 500. And so you can see that when we showed the theory back here, it did in fact, the range typically is about 20 to 500. Now, one of the difficulties is that people have observed that that's fine if you've got a nice monotonic decay of pore pressure, but sometimes you see this response where the pore pressures initially rise before they drop. And Professor Main referred to this as a dilatory response, so a soil that has more dilation, and so you get these lower pore pressures on the shoulder, and they rise up. So people have observed that when you measure pore pressure on the face, where it's dominated by the mean normal stress, you have a lot of shear stresses, but there's a very high mean normal stress, compared to just behind the shoulder, where the mean normal stress has gone through a reduction, and so it's dominated by shear behavior. And if the soil is stiff and is dilated, then you can get much lower pore pressures there, and they will initially rise up as you get sort of localized dissipation, not truly horizontal. And so Professor Main, with one of his graduate students, Susan Burns, came up with an alternative approach where they tried to break out the components of the measured pore pressure being made up of the hydrostatic and then the octahedral component, which essentially he got from spherical cavity expansion, and then the shear-induced excess pore pressure, which he got from sort of a cam clay model due to shearing. And so what he did is he looked at one-dimensional consolidation, cavity expansion, and applied the cam clay soil model to get the shear-induced excess pore pressure. And by doing that, he could predict these sort of dilatory type responses where the pore pressure would initially rise and then fall back. So here there's a comparison between this stiff clay from Italy, Taranto, heavily over-consolidated clay, where the pore pressure would rise and then begin to decay down to equilibrium. And so it requires curve fitting, where you curve fit, assuming different soil parameters for the critical state model and assuming different rigidity index until you match the curve. A little bit complicated, but it shows that it can handle that process reasonably well. Of course, sometimes you can get much more complex dissipations. Here's one where it's starting from a negative value and then rising up and then falling back down to equilibrium. You know, obviously a lot more difficult to interpret, and particularly those sort of theories that we just talked about, they can't handle this because now it's a negative starting. So the shear-induced pore pressures have to far exceed the octahedral, and the theories can't cope with that. And so real soil behavior is a lot more complex, and the pore pressure distribution is a lot more complex. And also you've got the risk that the sensor may not be 100% saturated when you're starting from a negative number. And part of the reason for this complex distribution is that back in '85, Professor Campanella and I and some others published a paper, and in that paper we showed examples of what the pore pressures around a cone look like, because some data in the literature where pore pressures were measured right on the tip, also measured on the face of the cone and then on the shoulder and then in a few locations behind the sleeve. So right up the very cone, and then the U1, U2, and U3 location. And here's a few examples. So the McDonald Farm, the normally consolidated clay, is essentially this green set of data. And so you've got an excess pore pressure. This is U over U0, so everything's normalized by the equilibrium water pressure. And so on the face of the cone, you know, it's maybe up to 3 or 4 times hydrostatic, and then behind it drops a little bit. But you can see when you get into more heavily over-consolidated clay, pore pressure on the face of the cone can get very, very large, 20, even 30 times larger than equilibrium. And the pore pressure behind can drop sometimes to actually negative values, or sometimes a positive value, depending on the type of clay, how sensitive it is, what the shear-induced pore pressure is relative to the octahedral. And so you can see Taranto stays positive, but like London clay went negative. So obviously a very complex distribution. And so you can see when you're trying to predict dissipation, if you've got very high pore pressures on the face of the cone and very low pore pressures behind, then initially there's sort of localized redistribution before it all starts dissipating radially away. And that often explains why there's a rise in pore pressure before it begins to decay away to equilibrium, particularly in the U2 location. So Sully and Campanella and myself back in '99 wrote a little paper that tried to help with this. And so Sully showed a number of plots suggesting a way to handle it, and suggesting essentially that it was easier if you plotted it on this square root time plot where we're expecting it to be a straight line plot. And so it would rise when the pore pressures rise up and then begin to decay down. You can join up the straight line portion and then extrapolate back to what you assumed the initial excess pore pressure would have been if you had not had this localized redistribution. So it was a recommended way of how to determine T50 when you had these more complex dissipations. What Sully also showed was that when you had very short dissipation. So if it would rise up and begin to dissipate, but it's a slow process, so you could just extrapolate that straight line portion on down and then back to get the initial distribution. And here's an example. This is at a site where on the left-hand side I'm showing the log time plot, and you can see initially rising and then beginning to fall. And of course, if you used Burns and Main approach, you could try to curve fit, but it's a little bit complicated. And so you can try and extrapolate back to try and get an idea of what you think it is, but obviously a lot of uncertainty when you're extrapolating this curve on a log time. But on the square root time, you can see that there's a nice straight line portion, and if you draw a straight line through that and extrapolate it back, it gives you a reasonable idea of the initial. And I've drawn these onto the same scale. They're both out to 100 psi. And so you can see the assumed initial distribution from the root time you've come across. That seems a reasonable match likewise on the log time plot. And so here in this particular case, I think T50 is about 350 seconds on this one. Here's another one. This is that one I showed before, the one that started from a negative value. So here I'm showing it on a log time plot, so negative rising up and coming down. You can see if on the log time plot, quite difficult to try and extrapolate back to some initial that would allow you to get the T50. Whereas on the square root time, there is enough of the straight line portion that allows you to join it up, extrapolate it back. And of course, if you come over and compare it on the log time, it's quite a reasonable number. So you can pull off the T50. So you can see on these more complex dissipations, often the square root time method is a little bit easier, taking this, the straight line portion of the curve. And what Sully also identified is that it was observed in those early days that when you did a dissipation test, sometimes, particularly in stiffer soils where the tip resistance could be relatively large, is that sometimes there was a sort of a rapid, almost sudden drop in pore pressure before it started to follow the linear line on the root time plot. And this initial rapid drop was associated with the unloading of the cone. So you're pushing the cone, there's obviously a load on it, there's stresses on the tip, and then when you stop, if you take the load off, of course the rods rebound a little bit, the load begins to drop on the tip, and so you pick up this unloading of the soil due to the release of the load on the cone. And so based on that, often the recommendation is to keep the load on the cone. In other words, clamp the rods so that you do not unload the rods. It's a big issue when you measure the pore pressure on the face because, of course, it's dominated by this normal stress from the tip being applied to the soil. Less of a problem on the U2 location, but sometimes you can still see it in certain types of soil. And so the general recommendation is clamp the rods to minimize that sudden drop in unloading. And you'll see the subsequent ones I show, we typically clamp the rods, and so during a dissipation test, and so you'll see that we don't suffer that problem. So the complex soil behavior makes the theories less than perfect. Most theories assume some simple stress strain model, either elastic, perfectly plastic, or some simple nonlinear stress strain curve, for example, like CAM clay, where real soil response is a lot more complex, highly nonlinear, often strain softening where soils are sensitive, and often rate and stress path dependent. And of course, the complex loading around the cone, the unloading around the shoulder that causes big differences between pore pressures on the face of the cone and just behind the cone. Now, in recent years, there's been quite a bit of work, nice work on rate effects, where looking at what the influence of changing the rate is, or another way to look at it, what if you've got soils that happen to have a coefficient of consolidation so that the standard rate of pushing happens to get you in a spot where there's partial drainage. So we assume that in clean sands, we have a drain penetration. So if you think of the right-hand side here, there's no excess pore pressure, and you get a high tip resistance. And then in clays, you have essentially undrained penetration, so the coefficient of consolidation is low enough that the penetration is essentially undrained, and so you get these large excess pore pressures. But there is a zone in the middle, and it covers almost 1.5 orders of magnitude of coefficient of consolidation, or at least on the tip resistance, maybe slightly over 1 order of magnitude of coefficient of consolidation, where you're in this zone of partial drainage. It's not fully drained and it's not undrained. And so there's been a fair bit of work on this, and Randolph did some of the early work and developed this dimensionless velocity, which is the actual velocity times the diameter of the probe divided by the coefficient of consolidation. I know it says CV there, but it should say CH. Now, for undrained penetration, nominally it's around a dimensionless velocity of greater than 1. It varies a little bit. Sometimes it's sort of, if you look at the pore pressure one could argue it's up around 30 to 50. But when you go into the equation, that determines that the coefficient of consolidation, it should be in the horizontal direction, is about somewhere between 10 to the minus 5, 10 to the minus 6, which essentially is a T50 of somewhere between 30 seconds and 60 seconds, so a half a minute to a minute. So if the time for 50% dissipation is greater than a minute, then typically you're undrained and you're okay. If it's less than a minute, you may be in the partially drained session. And so just recently, and I apologize for the loss of reference here, but this was some recent work by Schneid and Randolph in ASC just last year. And so they did a very nice piece of work where they looked at the effect of partial drainage. And they've sort of flipped that plot I had. Here they've got T50 on the vertical axis and CH on the horizontal. But they basically showed that Tay and Holsby theory matched very well, of course, when it was undrained penetration. But when T50 was less than about 30 seconds, there began to become a bit of an error due to partial drainage. And so essentially saying because of partial drainage, the excess pore pressure isn't as big as it should be. And so the time, the T50 that you record ends up being too large. And so there's an error. And so instead of getting T50s that maybe should be 1 second, you're getting something like up around 10 seconds because of the shift of the curve. And they likewise recommend that roughly when T50 is less than, they say 50 seconds, but nominally about 60 seconds, it's going to be influenced by partial drainage effects. And they actually said that they would recommend 100 seconds, so a little over a minute, to start modifying it. And so if you come back to the nomograph that I had used back in '92, where CH is on the vertical scale, T50 is on the horizontal scale, so you can see here it is in minutes. So now you can see why I stopped the curves roughly at about a half a minute, because that's when you start to get into the partial drainage. So I'd always sort of stopped it in that region, having a sense that that's the theory no longer applied up there. And so if you take I said Schneider, it should be De Jong and Randolph's relationship, you can see that the Tay and Holsby lines start to go essentially vertical here. So you can see all of the data that we collect from the field was well in the undrained region. And so when you look at the range of T50s, typically it's from roughly about a minute to about 500 or 600 minutes. Now remember, 600 minutes is roughly 10 hours. So a T50 of 10 hours, you have to wait a long time to get that T50 in very low permeability clays. But in a lot of the time, it's often in the sort of the 10 to 50 minute range. But anything less than a minute, and you do run the risk that partial drainage effects and the theory becomes unreliable, and the interpretation becomes less detailed. And essentially, T50 begins to lose its value. And you saw from the theory here that essentially for a single value of T50, you're covering now a very wide range of CH when you get to these very fast dissipations. So it becomes very unreliable in that region. So there's many uncertainties. The big one, initial distribution, particularly when you get into stiffer soils, over-consolidated soils. Non-homogeneity, so stratigraphy. So of course, if you've got sand layers above and below, or vice versa, clay layers above or below, then dissipation is not truly horizontal. You start to get some vertical dissipation affecting the results. And then you've got anisotropy and macrofiber fissures, etc. Fissures closing initially when you push the cone and then sort of opening a little bit as you recompress. Influence of non-horizontal dissipation, soil disturbance. So if you've got sensitive soils, you get a sort of a smearing around the cone, and Burns and Main did try to allow for that. They sort of incorporated a smear zone. And then, of course, the filter element potentially becoming clogged in those cases, or not 100% saturated. So a lot of uncertainties. It's not a perfect interpretation, but generally accurate to within about an order of magnitude, unless the soils are very soft and homogeneous, where it's a lot more accurate. So if you've got soft, normally consolidated clays, then you can get quite good interpretation. But anything outside of that, the stiffer clays, the silty clays, and the clay silts, and the silty sands that tend to be a lot stiffer, the dissipation curves are more complex and the accuracy less good, and so hence that's why I say within an order of magnitude. So anisotropy of flow, coefficient of consolidation is influenced by permeability and the sort of compressibility stiffness of the soil, represented here by the one-dimensional constrained modulus M. So the coefficient of consolidation is actually the permeability times the stiffness divided by the unit weight of water. Or if you've done a dissipation test, you've calculated C sub H, and now you want to estimate the permeability, then you can see that it's influenced by the stiffness, inversely by the stiffness of the soil. So the stiffer the soil, the bigger effect it's going to have on estimating the permeability. And then, of course, you've got the vertical to horizontal flow anisotropy. And Louet and Height in the Singapore workshop in 2003 presented some very nice data. Professor Main plotted it up very nicely. So you've got sort of the comparison between horizontal and vertical permeability and the one-to-one line, and showing the ratio between the two. Generally, you know, between most of the data is between 1 to 1.5, a relatively homogeneous clay. Sorry about that. And so the anisotropy is not too bad until you start getting into some of the varf clays, etc., when it can become quite significant. And so recently I updated the sort of chart for permeability. So here's a chart of permeability on a log scale against T50 in minutes on a log scale. And so what it's done is it's taken the Tay and Holsby relationship and then incorporated one-dimensional constrained modulus. And I've recently updated the correlation, the link between the normalized cone resistance and one-dimensional constrained modulus, embedded that into a single relationship. So the upper line here with the normalized cone resistance is about 2, is sort of a very soft, normally consolidated clay. It won't go much lower than that number. And then coming across to where the normalized cone resistance gets up to about 14, and then it stays about there. So there's the range. It won't go out much outside of that. And way back in the 80s, Perez and Farrell published a very nice sort of empirical correlation against permeability and T50, and there's their lot of relationship that they had suggested. And what was nice about their relationship is they had broken it up for clays and silts and sands, and so as you progressively went up the curve, as T50s got smaller and smaller, they sort of identified you were getting coarser and coarser material. And here I've marked, you know, roughly that T50 of half a minute, saying, well, you know, this is the region where it's undrained, where it will work. Once you get outside of that, it's going to be partially drained, and the T50 won't work so well. So there's the sort of cutoff at nominally about half a minute to a minute of T50 to cut it off. And the dots on here are those same dots that were from that 92 paper of sites around the world where people had measured coefficient of consolidation, but also permeability, and so we could plot those. And you can see it fits the trend quite well. So this is a little bit better in some respects because it does incorporate stiffness. It's sort of embedded in there, and it says that that will have an effect. Now, of course, some people do like to estimate permeability just based on soil type. And so since the CPT gives you an estimate of soil type, or more correctly, soil behavior type, you know, back for the CPT book in '97, we did suggest a range of permeabilities, and so you can give them average values and assign an average soil behavior type IC value. And so recently I sort of updated that and said, well, here was the range of permeability against IC that we had suggested in the CPT book in '97. And then if I just sort of simplify that with the red relationship, and then I can actually show the contours of permeability like these IC contours on the soil behavior type chart. And so if you go back, you notice back here that the limit of undrained penetration is normally about 10 to the minus 7 meters per second, maybe somewhere between 10 to the minus 7 and 10 to the minus 6, but conservatively at 10 to the minus 7. Then you come across here and you can see that 10 to the minus 7 roughly is where the value of 2.6 is. So the IC of 2.6, which is normally the cutoff that I've often said separates sort of coarse grain material from fine grain material, or drained material from undrained material, does work about right based on what you've seen there. And so you may recall from a previous webinar that I'd had sort of talked about a more generalized soil behavior type chart where I'd shown not only the drainage, but whether or not soils were contractive or dilative. And so zones A and B were essentially coarse grain materials where penetration is predominantly drained, and above the line in zone A they would be dilative, and below the line in zone B they would be potentially contractive. And then in the fine-grained soil region, in zone C, it would be predominantly undrained but dilative, and in zone D it would be fine-grained, undrained, and contractive. So you can see that this region D here is where the dissipation tests tend to work their best. So where you've got a contractive soil, you get large excess pore pressures, you won't get too much of an unusual shape out of it, and it will be predominantly drained. And I'd identified a transition zone here where you could get partial drainage effects. And there's some controversy about how wide that transition zone is. I've shown it relatively narrow. One could argue it could be a little bit wider, but you see on this log-log scale of the soil behavior type, it is a relatively small zone. And so if the data falls in or close to that zone, then that's a sort of warning that it could be partially drained. And then likewise, if you do a dissipation test and the T50 values are less than a minute, then it's confirming it is essentially partially drained. So the procedure to generally follow is make sure your pore pressure sensor is saturated. And although I've never really discussed that in detail, because it does vary according to the different manufacturers, so different cone designs have different saturation procedures, so you need to follow the recommendation from the manufacturer. And then of course you stop during penetration, record the pore pressure with time, and because it's logarithmic, ideally you want to record relatively frequently at first and then more slowly later on. But often people collect at the same rate, often either every second or every 5 seconds, and so you get a lot of data. And then fix the rods. So don't remove the load during the dissipation. So avoid changing the stresses around the cone by removing the load. So then, in summary, dissipation tests are a useful thing to do. They do provide you with an equilibrium piezometric pressure if you let the pore pressure dissipate all the way down to equilibrium, so you can get the piezometric pressure and also estimate the piezometric level and determine whether or not the profile is hydrostatic. And then the rate of dissipation gives you an idea, at least to within an order of magnitude of the coefficient of consolidation, primarily in the horizontal direction. And then you can actually convert that to permeability, although it does introduce an added level of uncertainty because you do have to estimate the one-dimensional constrained modulus to do that conversion. So there's sort of an added level of uncertainty added there. So that's why I say accurate to within an order of magnitude, unless the soil is soft and homogeneous, in which they fit the theories really quite well. Useful to perform at least one dissipation test in each CPT. It does surprise me when people go out and do CPT with pore pressure measurements and don't do a dissipation test. It seems such an easy thing to do, and it does give you some extra information. And it's very fast in sand layers, so if you're primarily focused on the equilibrium piezometric profile and you do have sand layers, then stop in those sand layers, and it's quick and easy. And it does, in fact, help resaturate the sensor. So if you're pushing through in either very stiff clays or some stiff, dense, silty sands, and you develop negative pore pressures and you're worried that they, in fact, have created air bubbles in the sensor so that it's not 100% saturated. If you stop and do a dissipation, then it'll come to equilibrium. And of course, if you're below the water table, that's a positive number. And of course, the further below the water table, the bigger that positive number. So the faster those air bubbles will go back into solution. And the sensor will actually resaturate itself, and then you can carry on pushing. So that's sometimes a helpful way. And it's helpful to evaluate the time delay for pile load testing. So, you saw from the theory that the rate of dissipation is controlled by the radius of the probe squared. And so, for example, if you're in very low permeability clays and dissipation tests are taking a very long time, then there is an advantage of using a slightly smaller diameter cone, either going from 15 square centimeter down to a 10 square centimeter, or even down to a 5 square centimeter, so it's a little bit faster. But the radius doesn't change an enormous amount when you change the size of the probe, so not that big a help if you've really got slow dissipations. But another application is if you're driving piles and you've got clay and you know you're going to generate large excess pore pressures, then you can estimate the time that it will take for the pore pressures to dissipate around the pile simply by doing a dissipation test with the cone and taking the ratio of the radius squared, or the diameter squared, of the cone and pile. So, for example, if the pile is 100 times larger in radius than the, well, let's use 10 as an easy number. If the pile is 10 times larger than the cone, then the time to get to equilibrium will be 100 times longer than the Cpt. So if you're going to do a pile load test and you want to make sure that the pile is set up adequately, then dissipation test from the Cpt is a very nice way to get a handle on that time period that you may have to wait for the pile. And you can clearly see that if it takes, say an hour to dissipate the excess pore pressure around a cone, and the pile is significantly larger, you can see that you might have to wait hundreds of hours for that pile to fully set up before you do the pile load test. But at least it's a very simple test to get a handle on exactly how long that's going to be. Most of the time, people are just guessing that they do a pile load test maybe a week after driving the pile. It's a somewhat arbitrary number. It obviously should depend exactly on the type of soil. So that concludes the main part. So we've got time for questions. But what we can do is I can switch across and see if I can show a few examples. So you can see I've resolved the issue about how to get the program to work first time. And that's by running the PowerPoint on the Mac side of my computer. So I'm just going to show you an example. This was a project that came in actually just a few days ago. So it turned out to be a very nice set of data, and so it's a nice example. I'm just going to make the plots a little bit bigger here. So this is a site that, as you can see, we look at the corrected data. It's essentially clay with some sand layers, a little bit sandy near the top for the upper 4 or 5 meters, and then essentially clay with some sand layers at around 15 to 17 meters, and then some others. If you look at the overlay plot, very consistent site. There was 3 soundings. They all look essentially the same. A series of dissipation tests. You see they're marked here on the pore pressure. So on this particular one, there was one around 3 meters, then one a little over 9 meters, and then one at 15 meters. So the one at 3 meters was right on this sort of mixed ground conditions of sandy soil with clay, sort of interbedded sands and clays. A little bit complex up there. But the one at 9 meters, a little bit better. This is predominantly in this clay, a somewhat more homogeneous clay. And then the one at 15 meters is essentially predominantly in this sort of sandier zone. And if we look at the estimated parameters, if I go across and look at the estimated OCR, you can see that at 9 meters, the OCR is around 3 to 4. So the dissipation test at 9 meters was in a slightly over-consolidated clay. So if I now go and look at these dissipation tests, here they are. So here's the one at 3 meters. So you can see it's rising from a negative value, rising up, and then turning around and coming back down to equilibrium. And then the one at 9 meters, rising a little bit and then dropping down to equilibrium. You see after 1,500 seconds it was stopped, so it didn't get to equilibrium all the way. And then the one at 15 meters, much more rapid, dissipating essentially 100% in about 100 seconds, so just a couple of minutes for 100% dissipation. And those were all plotted on a log scale. And you'll see that the first one was plotted from -50 to +50, where the others were -50 to 500. I often quite like to plot them all to the same scale. So there is a nice feature in the software that you can just force them all to go to the same scale. So now if I go back to the first one, now you can see it on the same scale. So you can see just a little bit of negative rising up. You see that's actually quite hard to interpret that unless you do change the scales. So you can see why I blew the scale up to get a little slightly better look at it. So let's go with the one at 9.5 meters. This is the one predominantly in the clay. And so you can see that getting the T50, not that easy. There's obviously some projection of where the initial excess pore pressure is, and then it comes down. So T50s, it's roughly, T100 is almost 70 kPa, and the initial is up over 500. So there's like a little over 200 between the two. So it's up around this 300 to 400 mark. So it's around a couple of hundred seconds is where the T50 is going to be, but it's a little bit difficult to interpret. So the program, you notice it's on log scale. The program, in a way, prefers that you look at it in square root. So if I'll just switch it back to square root. So here's the square root time plot, and I'll just go up scale a little bit. So square root equal to 50. So a little over 1,000 seconds. So now you can see a slightly easier curve to interpret, and the program has a system where you can draw a straight line portion to match the straight line portion. So you sort of try and line it up as best you can. Here I'm doing it rather quickly. And then you ask it to calculate, and it calculates that the T50 is roughly at about 320 kPa, which is about 326 seconds. So I said it was around 300 to 400 seconds, and so you can see there it is at 326 seconds. Now you see the program has to assume a rigidity index, and so it does that automatically, and so you can go up and check how it did that. And so what it does is it estimates the small strain shear modulus and estimates the undrained strength and calculates a rigidity index based on that small strain modulus, and you see it comes out about 500. Now you might think that that's maybe a little high because it is an over-consolidated clay, and from Kaveni's Mitchell's work, it would drop a little bit with OCR. So let's just move it down to 100. So see how it changes. If you look in the bottom left-hand corner, currently it's calculating about 5.8 times 10 to the minus 6 meters per second. So 5.8 times 10 to the minus 6 with a rigidity index of a little over 500. If I change it to 100, it recalculates it. So I ask it to recalculate. Oh, sorry, I didn't actually. Got to tell it to do that. So let's go to 100, tell it to do that, and it recalculates. And it dropped to 2.5 times 10 to the minus 6. So from 5.8, dropped it down to 2.5 by changing that rigidity index from 500 down to 100. So not a massive difference, but it illustrates the uncertainty in CH when you do that. And with that number, the projected coefficient of permeability in the horizontal direction is about 1.5 times 10 to the minus 9. Now, out of interest, we can come across and look at the estimated permeability, and here's the estimated permeability. So it was at 9 meters. So it would plot just about here between 10 to the minus 9 and 10 to the minus 8. And based on soil behavior type was estimating at about 10 to the minus 8 meters per second. It's actually not bad agreement between those two. So you can see the square root time is a little bit better. and easier to use. Now, the program does have a nice feature that when you've done this interpretation, it now begins to show the estimated initial excess pore pressure is the circle, the red is the starting point, and then the triangle is the equilibrium. And so if you do that for all of them and compare those triangles with your assumed hydrostatic, you can determine whether or not it agrees with the hydrostatic. And if it doesn't, you actually have the option to manually change U0. So I can move it up and down. And of course, T50 changes and the calculation changes. You can see that happening there. So the program does allow you to look at those quite easily. And you can do that on all the interpretation. So here's this one that's in the sandier material. The log time, very, very difficult to interpret. So let's just switch over, move, switch the axis, then go back to here. Now it's on the square root time. So that more complicated one now doesn't look so complicated on square root time. And very quickly line up the initial portion, ask it to calculate, and there's the T50. You can see it's 9 seconds. So it's basically saying, well, that's well below 60 seconds. So there's a strong likelihood that this was partially drained. And that's consistent because it was a sand layer at 15 meters right there. So it is a sand layer. So not surprising that it gets interpreted as being a partially drained penetration. Okay, so let's get back to the questions and see what people have said. First question, is it better to reach T90 or T80 in order to obtain a more accurate CH, or do they give similar values? Good question. The answer is it depends on how closely the theory matches the measured. And I didn't show it, but a new feature that we're adding into Cptu is a curve fitting feature where you can press a little button, but once you've done your interpretation, I think, yeah, it's on this one. There's a little button where you can add the curve fitting. And so the red line is matching the theory with the measured. And you can see it matches it pretty well. But down around the T80 and T90, it's not matching so well. And so in this particular case, it would really illustrate that using T80 or T90 wouldn't give you the same answer as the T50. The reason now people have homed in on T50 is twofold. One, of course, you get there faster, a lot faster, about 30 to 40 times faster than it will take to get to T80 or T90. And secondly, the soils are going from that recompression mode to the normally consolidated mode, or to the stress history that exists in the ground. So if the soil is over-consolidated in the ground, in the initial stages it's more over-consolidated, and then slowly gets to the spot where it's at the stress history that it is in the ground. So T50 is nominally that spot where it matches the in situ conditions. Of course, not perfect because the theory's not perfect. Next question, G is at 1% and not a very small strain. Why 1%? No, I didn't say G was at 1%. I just gave the example and said if you looked at the definition of rigidity index, then Professor Main had quite nicely shown that the inverse of rigidity index is this reference strain, which if it is a simple, elastic, perfectly plastic, it's where the material reaches failure. So for an elastic plastic material, it's where it reaches failure. So then I said, if you assumed a rigidity index of 100, then that calculates out as a reference strain at failure of 1%. Now, obviously, if the rigidity index is 500, then it's 0.5%. And that's the elastic plastic. Now, most people for nonlinear are taking something sort of halfway out to peak. And so that's why this sort of rigidity index at 50% of the failure load comes in, which is where you get these numbers. But the rigidity index clearly has uncertainty for real soils where it's a little bit vague about exactly what its definition is, because modulus varies nonlinear with strain, And so it's a little bit unclear about the exact definition of what rigidity index should mean. But there is somewhat of a move that people are tending to lean more towards a smaller strain G. I wouldn't go as far as saying that the G0 or G max over SU is the correct one, because those numbers seem too big. From our practice, those numbers would appear to be too big. And typically, I would drop those numbers often by about a half or a third to get to a more representative strain value, which clearly depends on the rigidity index. So next question, are negative pore pressures possible in highly dilated soils? And the answer is absolutely yes. I showed you some examples, and here is one. Now this happens to be on a boundary. This data, and I interpreted it a little bit later. There it is. I didn't highlight that. At the bottom it says it's on the border between an overlying sand and soft clay. So the profile here was some upper sand and then transitioning into a lightly over-consolidated clay. But right at the transition, there appears to be a crust on the clay, and this dissipation test appears to be done right there. So probably the clay right at this depth is more over-consolidated. But more importantly, the pore pressures were negative pushing through the upper silty sand, and they were positive in the underlying clay. And so hence you're seeing this sort of macro layering effect where the negative pore pressures are where it's still being somewhat influenced by the sand, but of course beginning to be influenced by the clay below where you got these positives. So it illustrates that you get these very complex dissipation curves. So it's not unusual to see negative pore pressures. And I think when I went to the actual example, I think on this example, the first one did in fact start negative. If I blow that up a little bit, you'll see it a little bit better. So you can see it did start slightly negative and rose up. And this one was at 3.2 meters. If we go back at the profile, 3.2 meters here, you can see it's there was a little bit of a clay layer and then into sand. And so right at 3.2, you're just pushing into the sand. Pore pressures went negative, but there are some positive pore pressures probably above, and maybe even in the, well, probably certainly above where the dissipation test was done. You got positive pore pressures, so you get that more complex dissipation curve starting from negative. So yeah, it's certainly positive. This is good data, and that's a good example. Next question, rate is the role of strain path modeling of CPT behavior. I'm not quite sure what that question means, but certainly as the theories get more comprehensive, as people are doing more detailed finite element analysis using more comprehensive constitutive models, people are getting a better handle of the initial pore pressure distribution and therefore the dissipation test. But I think you're still going to find that doing complex modeling to interpret dissipation tests is not going to be what everyone's going to do on a day-to-day basis. So they'll still tend to use these sort of more simpler interpretation methods to get an idea of the coefficient of consolidation for design purposes. Now, when you compare it with lab data, of course, remember often it's hard to get truly undisturbed samples, hard to get a lot of them, it's expensive. So samples are not always truly undisturbed, and then putting the samples into the lab, often it's quite difficult if you actually want to get the horizontal coefficient of consolidation, if that's the one you need, either for pile design or wick drain design, where the horizontal one is the one you want for design. If the vertical one is the one you want, then of course lab testing can be quite useful. So for high-risk projects where the budgets warrant, it's obviously nice to do CPT, some dissipation tests, followed up by selective sampling and high-quality lab data to compare the two. Next question, what is the best way to check CH estimated from Cptu? He was comparing it to lab value of CV multiplied by the ratio of CH to CV obtained from literature, but gets lots of deviation. Yes, I mean, that's just as I said. I mean, how do you check it? And for low-risk projects, where often you just can't afford to do the lab testing, then you don't have anything much better than this, but you do have to keep in mind that it's an accuracy to within about an order of magnitude. So although we're often calculating, as you see in this example, where it says, 1.045 times 10 to the minus 5, I don't get too carried away with the decimal places in the calculation. It's essentially 10 to the minus 5 meters per second, plus or minus a half order of magnitude. Now, when you do lab testing, for the high-risk projects, you want to get high-quality samples, do high-quality lab testing, and for higher-risk projects, you can actually do lab testing in the different directions to try and get a handle of the anisotropy. Next question: how might partial drainage affect liquefaction screening and evaluation? Well, that's slightly off topic, but it sort of does. It's captured in a way in this chart where it sort of says, okay, most of the liquefaction screening for sands is up in region A and B. Most of the data for case histories of liquefaction is in sands in region A and B, and it's only in the very silty sands that begin to get into this region of partial drainage. But if you come back to here, which way am I going? Yes, the rate effects. Partial drainage doesn't have a massive effect on the tip resistance. So, for example, if you're drained and you start to get partially undrained, the tip resistance begins to drop a little bit. But it doesn't drop a massive amount if there's a little bit of buildup of pore pressure. You have to get a lot of buildup in pore pressure for a big drop in the tip resistance. So if there's a little bit of excess pore pressure, the tip resistance will drop a little bit, and therefore it'll plot slightly lower on the chart, which means you'll tend to be slightly more conservative. So I don't think it's a big issue. When you start getting into this transition zone, if you've been reading the stuff and you watch the webinar on liquefaction, I did identify that there's this transition zone from essentially drained to undrained behavior that does get a bit tricky. How do you explain negative equilibrium pore pressures after dissipation tests? Well, sometimes if you do a dissipation test and you truly get to equilibrium and it's negative, then that often applies you're just above the groundwater surface, or above the piezometric level. And so the soil could be saturated, but you're coming to equilibrium at slightly negative values. Of course, there's also the risk of misinterpretation if we go back and look at some of these interpretations. So here's an example. So if you were doing a dissipation test, the pore pressure is rising, and then it begins to level off. There is the risk that when it levels off, you think you've come to equilibrium and you stop. But of course, it might be leveling off, ready to go back down again. So you have to be very cautious about these more complex ones that you did in fact wait long enough. And of course, remember, this is a log time, so it stayed constant there for a couple of minutes. So if you were just recording pore pressure with time, there is the risk that you think it's come to equilibrium, but it may not have. So you always have to question with these complex shaped curves, especially coming from negative and rising up, about whether or not it's truly got to equilibrium yet. Now the question here is, of course, negative pore pressures in a dense till, and so I'm assuming it started negative and never went positive. It's hard to imagine that maybe it started at a very high positive number and then eventually ended up at a negative value. Of course, there is always the chance that the zero drift on the pressure sensor drifted a little bit off, and the accuracy of the pore pressure may not be so good. And certainly when you're measuring pore pressures close to zero, then you're going to lose some level of accuracy. A lot of pressure transducers have accuracy of a plus or minus 10 kPa, depending on the size of the transducer. And so you can be a few kPa off, which can be a few centimeters off in the head of water. What type of pore water pressure response can be expected when pushing through contractive type soil? Well, in general, if it's a contractive type soil, pore pressures are going to be positive, and you're going to get the types of dissipation, the monotonic ones, particularly if it's highly contractive. But it depends on the pore pressure location. But I'm assuming the question is the more typical U2 location. And so if it is a contractive soil, you'll typically see close to a monotonic dissipation. Although, as you saw here, I mean, the soil here, well, okay, it was lightly over-consolidated, so it did rise before it dropped. Next question. Reference for determining time delay of pile load test. There aren't, I mean, those references are dispersed in many different places. No one's specifically written a paper on it, but a lot of papers often do make a sort of a passing comment about this. I did check on the guide. I think the guide does have a sentence related to it, where it basically says that, you know, the coefficient of consolidation is controlled by the radius squared, and so if the coefficient of consolidation of the soil is unchanged, but just the radius changes, then it's the ratio of those radius squared. And so it's a fairly well-known observation, but you're right, not often written up on. No data conversion tool for importing dissipation tests into Cptu. Is this being developed? When we say data conversion, when you're loading dissipation data in to Cptu, you know, the data I was reading in was in Excel, and so, you know, you go to the Excel sheet in our particular case, and Greg collects the data. Now it's in PSI, and every 5 seconds. So column 14. So you put in the data begins at line 2. You put in the depth. Time column is 14. Pressure is 15. And so here I'm using metrics. So then you have to convert PSI to kPa. So you do the conversion you know, when you're loading in the data. So as long as the dissipation data is in either a text file or in an Excel file, then you can manage most of it. You can convert time or you can convert the pressure to load in the data. Okay, just to finish off, how do you get accurate horizontal permeability in highly dilated soils? Very difficult. You know, the best way, of course, ideally, the best way to get permeability is to do a pumping test or to do a larger scale test. But full-scale pumping tests are expensive, which is why piezo cone tests are often attractive, you know, because if you're going to do CPT anyway, then the dissipation test becomes, you know, almost for free, as it were, which is what's so attractive about it. There are a variety of tests you can do. You know, with CPT equipment, you can push in groundwater sampling devices, which are essentially a bit like standpipe piezometers, and you can do slug tests, you know, where you can do a falling head or rising head permeability tests with devices that were pushed in with CPT equipment. So there are a variety of backup tests. So once you've done the CPT, you've identified the stratigraphy, you've done some dissipation tests, you've got an idea what the equilibrium groundwater conditions are and what the coefficient of consolidation and permeability are estimated to be. And then you could, based on that and based on the stratigraphy, you can select appropriate parts of the soil profile where you might want to do an additional test, and you could move over, push in one of these very simple groundwater sampling devices, and then expose a certain element of the slotted section, and then run a either falling head or rising head permeability test. I'll make a little comment here that some publications about using very sensitive pressure transducers to do very accurate dissipation tests, but the warning is if the T50 is less than about a minute, then the theories become unreliable because of partial drainage. So a little bit of cautionary note about those. So would you consider it reasonable to degrade G0 values to failure using the hyperbolic relationship? Yeah. Yeah. So you saw from the software that, you know, when you're interpreting data, that you do have this option of going up into the calculation mode, and CPT says, well, at this particular depth, G0 in this case is like 47 megapascals, SU is 88 kilopascals. So it calculates the ratio of those two and puts it here. Now I've told it to go, so I'll have to go to one of the other depths, whereas we can still read that. Let's go to one of the other ones. So um, look at the settings up here, calculation settings, and oh, sorry, I think I set them all to 100. So let me just check this last one, see if this one's working. No, I set them all. Doesn't really matter. But Cpt gives you a little bit of a guidance by showing you what the values are. So in this particular case, there's the two values of G0 and SU. Oh, there's the calculation, yeah. Rigidity index is below. So there's the ratio between the two. So that's 30 megapascals. So it's 30,000 kilopascals over 51 kilopascals. So hence the ratio is almost 600 rigidity index. So that gives you a guidance of how much you might want to soften it down a little bit. And if you look at that Caveni and Mitchell from one of the earlier slides there, you can see that for the types of material that they were suggesting, they were had nothing as high as rigidity index as high as that. And so you might want to soften it down a little bit. 600 seems a little bit high. Yeah, but you can, the nice thing here is you can try different values and see what effect it has. It only takes a couple of seconds to try 3 or 4 values and run the interpretation to get a sense of how sensitive the answer is to that. So one of the last questions, is there a direct application for pore pressure tests for design of PV drains? Yes. If you go to the guide, right at the back of the guide on the application section, there's a little bit about wick drain design, about how you take the C sub H from dissipation tests and put it into the design of vertical drains. So, okay, truly last question. How good is Cpt at determining C sub H compared to other parameters on the table? Rating K through 5. Can you add Cn to this table? Not quite sure what that. Oh, Ch to that. Got it. I see. I think the question was related to. I think it may be related to this table, where it's showing permeability, and could you show Ch? You could do, but right. Yes, in the guide there's a table that rates it, and I think you're right. I don't think I include C sub H in that. I'd have to double check, but how good is it? Well, I basically said when you do a dissipation test, it's to within an order of magnitude. So nominally, plus or minus a half order of magnitude is the accuracy for most dissipation tests, unless it's a soft, homogeneous, lightly to normally consolidated clay, where the theory is likely to work a lot better, and then it's likely to be a little bit more accurate. But generally, plus or minus